Welcome back to the Deep Dive. Today we're tearing into a concept that uh, sounds pretty technical, but it's actually the bedrock of our connected world, packet switching.
It really is kind of the invisible engine running everything. Our goal today is to, cut through the jargon and really understand this idea. It's what took communication from being expensive and rare to this global thing we use constantly.
Yeah, think about it for a second. Just try to imagine a world where every little piece of data, like a photo or even just a quick text, needed its own private, dedicated phone line.
Which is exactly how it used to be, more or less, before this big shift.
So we're diving into how we made that huge leap, how we got to this seamless digital life.
Exactly. It's why everything online feels so easy now. It's the foundation for that easy digital lifestyle we all kind of take for granted.
Totally. What was the first connected thing you touched this morning? Checking messages, maybe streaming some music. Well, we're exploring the tech that makes all those millions of data points just show up instantly and affordably.
Okay, so let's set the scene. Before packet switching, what was the problem? Our sources paint a picture of communication being, clunky.
Very clunky.
Yeah.
And expensive, based on an old system really designed for something else entirely, right?
Exactly. It was called circuit switching. Think old school telephone calls. And the sources really point out three big problems with trying to use that for data.
First one that jumps out is just the cost.
Yeah.
It was seriously expensive because you were basically renting a wire.
That's right. You reserved a physical connection end-to-end for your whole call or data session, and it was tied up just for you, whether you were actively sending anything or not.
Wow.
Yeah, and get this, the sources give a pretty stark example. Back in the 1960s, a simple 3-minute phone call across the country could cost what amounts to like $40 today.
$40 for 3 minutes. Okay, so not practical for constant data.
Not at all. And that leads to the second problem. Massive inefficiency, especially for computer data, which tends to be bursty little bits here and there.
Right, not like a continuous voice call.
Exactly. The analogy used is reserving an entire 6-lane highway just for one car carrying one letter.
Oh, okay, I get that.
Most of the time, that highway is empty, totally wasted capacity. But it's still reserved, still unavailable for anyone else.
So high cost, super inefficient use of the lines that naturally creates a bottleneck, right?
That's the core issue. Circuit switching required exclusive use of these lines. So building a massive global network where, everyone could communicate easily, impractical, unsustainable, really. You just couldn't scale it.
Okay, so the stage is set for a better idea. And this is where the big conceptual shift happens. Someone asks, what if we don't reserve the whole line?
Exactly. And the answer was packet switching. It's a fundamentally different approach.
So how does it work? Break it down for us.
Well, instead of sending data as one continuous stream over a dedicated line, you break your message email, web page, video chunk, whatever, into these tiny, independent pieces. Packets.
Little digital envelopes.
Sort of, yeah. Each packet gets a little header, like an address label, saying where it's going, where it came from, and what part of the original message it is.
And the key difference is, these packets don't travel together on one reserved road.
Precisely. They get tossed out onto the shared network infrastructure. Think of it as the public internet highways. They travel independently.
Wait, independently. So my email might get broken up, and part of it goes through, say, Chicago, and another part goes through Dallas.
Absolutely. They find the best path available at that instant. One path might be congested, so some packets zip off down another route. They all find their way to the destination eventually.
That sounds, a bit chaotic.
Yeah.
If they all travel separately and arrive at different times, how do you guarantee everything gets put back together correctly? And what about, errors or lost packets?
Yeah, that's a crucial question. It seems chaotic, but there are rules, protocols, things like TCP/IP managing it all. When packets arrive, the receiving computer checks them.
Checks for what?
It checks sequence numbers to put them back in the right order. It checks for errors using something called a checksum. And it checks if any are missing.
Okay.
If a packet's missing or damaged, the receiver sends a quick message back saying, hey, resend packet number 157. If they arrive out of order, it just waits and reassembles them correctly. It's like digital stitching, really.
Okay, that makes sense. So that ability to handle the chaos, to reassemble reliably, unlocks some huge advantages. What's the first big one?
Number one is just sheer efficiency. Because everyone shares the network lines, the capacity is used much, much more effectively. No more empty highways.
Right, multiple cars using the road at the same time.
Exactly. Second, and this was huge for the early developers, is resilience. If one connection, one router somewhere in the network fails,
The packets just go a different way.
yep, they automatically reroute around the problem. There's no single point of failure that takes down your whole connection.
Hmm.
This was critical for defense applications initially.
Makes sense. And the third benefit, the one that really impacts us all every day.
Cost effectiveness. Dramatically lower costs. When you don't need dedicated, expensive lines tied up for single users, the whole economic model changes.
And that's what opened the floodgates.
That's what democratized access. It made the internet affordable for universities, then businesses, then eventually, well, everyone. It's the engine behind that easy digital lifestyle.
So we have this brilliant idea. Who actually built it first? Who proved this packet concept wasn't just theory?
That really goes back to ARPANET, the Advanced Research Projects Agency Network. Our sources pinpoint 1969 as the year they first successfully implemented packet switching.
Connecting just a few computers initially?
Started small, yeah,
Yeah.
4 universities. But the key thing the sources highlight is why ARPA funded it. They needed a communication system that could survive damage, for research and defense, a network that wasn't centralized.
So that resilience wasn't just a nice side effect, it was a core requirement from the start.
Absolutely. And that resilience comes from this idea of intelligent routing.
Meaning the network itself is smart about sending the packets.
Kind of. The routers, the connection points in the network, are constantly talking to each other, monitoring traffic. If one path gets jammed up with data...
Like a digital traffic jam.
Right. The routers tell incoming packets, maybe try this other route, it's clearer. So packets dynamically shift to less crowded paths. If a cable gets cut or a router fails entirely, the system just routes around it automatically. It's designed to be self-healing.
And that flexibility, that ability to work around problems in different paths, that's what allowed it to grow into a truly global network, connecting all sorts of different computers.
Yes, that was crucial. It didn't matter if you had an IBM mainframe talking to a DEC mini computer running completely different software. As long as they both could speak the language of packets, break data down, address it, send it, receive it, reassemble it, they could communicate.
So the underlying tech didn't have to be identical.
Didn't matter. That interoperability was key. We found a great quote that sums it up. The beauty of packet switching is its simplicity. Send small pieces independently, trust the network to deliver them, and reassemble them at the end.
Simple idea, massive consequences. Okay, let's bring it home. How does this invisible engine power our lives today? This is where we really feel that easy lifestyle it enables.
I mean, it's literally everywhere, working constantly behind the scenes. Every time you stream a movie, send a WhatsApp message, join a video call.
Billions of packets flying around.
Billions upon billions, shredded, sent, stitched back together, all in milliseconds, so it feels seamless to us. We don't see the packets, we just see the result.
And something like streaming high-definition video must be an incredible test of this system. That's a ton of data.
It's a massive continuous flow. Millions of packets have to arrive in the right order with minimal delay for that picture to look smooth. Without the efficiency of packet switching, sharing those lines, services like Netflix or YouTube, or even just reliable video conferencing for work, they'd be technically difficult and probably way too expensive.
So it's not just about getting data there, but getting it there efficiently enough for these demanding applications.
Exactly. And now we're pushing it even further. Think of 5G.
Right. The promise there is super low latency, almost instantaneous communication.
And packet switching principles are still core, but with new tricks. Engineers use techniques like network slicing within the packet network to create virtual dedicated lanes, guaranteeing that super fast, reliable connection needed for things like, say, remote surgery or autonomous cars talking to each other. Milliseconds matter there.
Wow. And what about the Internet of Things, all those billions of tiny devices coming online?
Another perfect example. Imagine trying to give every smart thermostat, every sensor on a farm, its own dedicated circuit switched line. It would be impossible.
A nightmare.
But packet switching handles it beautifully. These devices usually send tiny bursts of data, a temperature reading, a status update. Packets are perfect for that. They zip across the shared network without needing a constant open line.
So the system keeps evolving. Engineers are constantly tweaking the protocols, making them faster, more secure.
Always refining, meeting the next demand, whether it's for AI data flows or maybe even quantum networks someday. It's robust because the fundamental idea, decentralized packet-based communication, is so flexible.
Which brings us to the end of this deep dive. Its clear packet switching isn't just, some obscure protocol. It's the foundational architecture for modern life. It makes global communication possible, affordable, and underpins that easy digital world we just expect now.
Its impact is huge. By breaking away from those old, controlled, dedicated lines, it shifted power. It democratized access to information and communication in a way nothing had before. It connected people, fueled innovation.
Yeah, it really enabled collaboration on a global scale.
And the real genius, I think, isn't in some overwhelming complexity. It's the elegance of the simple idea. Break it down, send it out, trust the network, put it back together. It's order emerging from managed chaos.
A brilliant solution that truly changed how humanity shares knowledge.
It really makes you think about what other simple, elegant ideas might be running things behind the scenes.
Absolutely. So next time you stream something, send a message, check your smart home app, just take a moment. Think about those billions of invisible packets making it happen for you. What other elegant, simple solutions do you think underpin our modern world? We'd love to hear your thoughts, maybe based on the sources we touched on today. Let us know what surprised you.